Okay, today I wanted to go through some continued problems in section 5.1, as well as talk about the final two remaining topics of the section, dealing with absolute values and what we refer to as complex derivatives using natural logarithms. I wanted to do a couple of examples from the homework first, number 54, 56, and 58 as examples. This is to reinforce the different ways you can use the properties, as well as how to kind of mentally approach a lot of these kinds of problems. And then afterwards, we'll discuss our two remaining topics. And your homework is up at the top. 55 through 73 odds, 83 through 95 every other odd, 101 and 103. Of the homework, the last two problems are going to be the toughest because they involve the complex differentiation. But there will be one of those specifically written for the test. Speaking of which, the last test was pretty good. I'm still about 3/4 way finished grading the ones that I have and getting some of the homeworks in that some people have turned in late. Those should all be in before I go to sleep tonight. So look for your grade to be fully updated by the time, by tomorrow morning, essentially. Because I never know what I'm going to go to these days. Okay, let's take a look at number 54. We're going to do a few examples first, because I think it'd be a good idea to reinforce some of these techniques, as well as remind ourselves of some geometric and derivative rules. Okay. So for 54, we have y equals the natural log of the square root of x squared minus 4. For this problem, I'm going to showcase a couple different ways you can do it. One that's kind of the common way, and one that's the not common way. Okay, so first of all, the primary step you should do in these kinds of problems is to rewrite. Is to see how you can use logarithmic properties to rewrite functions like this into an easier form. And so the first thing I'm going to do is I'm going to rewrite this using a power. So this becomes natural log of x squared minus 4 to the 1/2 power. And then now I'm going to use the power rule for logarithmics. And the power rule states that any powers can be moved to the front as coefficients. So this is another rewrite. Y equals 1/2 natural log of x squared minus 4. At this point, I could go ahead and take the derivative as the instructions state for me to do. However, you have many options on how you want to approach some of these problems, and some can produce some very interesting results. So at this time, I'm going to go ahead and do it the way we've been talking, and then I'm going to showcase one other that is allowed, it's just different. Okay? So if I take the derivative now, so I do d dx of 1/2 the natural log of x squared minus 4. The 1/2 can essentially pop out, and then I have to take the derivative of the natural log. The derivative of the natural log becomes, if you remember, oops, camera, no. Okay, this becomes our u, and remember the derivative is u prime over u. That's our u substitution formula. I believe it was theorem 5.2. And so we do, on top of a fraction, u prime, so the derivative of the inside would be 2x. On bottom of the fraction, we just put u, x squared minus 4. And then we combine any like terms we can and simplify. So if I combine like terms, the 2 and the 2 are going to cancel, leaving me with x divided by x squared minus 4. And so there's our derivative. And this is one perfectly acceptable way to do this problem. But now I want to showcase kind of one other way that doesn't break any rules and still gets the solution, just not exactly in the way you might think. So at this point in time, some of you may see inside this thing, this is actually a difference of squares from Algebra 2. And because it's a difference of squares, we can rewrite this in factored form. We can rewrite x squared minus 4 as x plus 2 times x minus 2. And if we choose to do that, our function changes. 1/2 ln of x plus 2 x minus 2. The reason our function changes is because we can transform multiplication using one of our properties. There's a property of logarithms which states that multiplication becomes addition. And so what we can do is we can rewrite this as d dx of 1/2 times ln of x plus 2 plus ln of x minus 2. This is a little nicer because the u's are much easier to do. So if you ever have a problem where doing the u prime over u is difficult, you may want to see if perhaps it factors, because this is an acceptable way to do this problem. It's just different. And so if you actually do this problem, you would have the 1/2 out front. Ln would become 1 over x plus 2. We still have to do u prime over u, but u prime would be just 1 plus 1 over x minus 2. And these two are actually the same thing. They don't look the same, but if you combine them together using properties of algebra, they end up becoming the same. And so this is a really unique way to approach the problem that will give the same solution just in a very different visual form. And so because of these properties of logarithms, there are often many different paths to get to a solution and many different ways the solution can appear. You have to be very conscious whenever you look at a problem of where do I want to stop? Because in theory, I could stop here. I could just take what is given and solve it by using u prime over u. But then I'd be forced to do a chain rule inside of this function, which can get very nasty very quick. And so if I'm willing to take the steps to rewrite it, notice how simple this was by comparison as to doing the chain rule with that kind of square root of x squared minus 4. And so this is just an alternative approach. Now, most normal people would definitely choose this first path. That does not mean the second path is not an option. It is just different. Okay. Let's go ahead and take a look at 56. Okay, 56. So 56 says y equals the natural log of t times t squared plus 3 cubed, close bracket. Okay, again, I could immediately go to the u prime over u version, but if I do that, u prime, I'm going to have a product rule because I have t times this parentheses, and then that parentheses is going to have a chain because it's a power of 3 with something inside of it. And that chain is going to have something inside of it, the t squared plus 3. And so that sounds complicated. That sounds annoying. The nice thing, though, is I can simply rewrite this function using a whole slew of natural logarithmic variations. So the first one I want to do is I'm going to split this multiplication problem into an addition problem. Ln of t plus ln of t squared plus 3 cubed. Already this is much easier. This one, for example, is a basic logarithm, so I could just write it as 1 over t and be done. This one, while not basic, is easier than the original. There's no more product inside of it. It's just a chain now. But even so, I can rewrite again. Using another power rule, the first one's good, but this next one, I have a power inside of it, which I can bring out front as a coefficient. Now, this first one cannot be easily rewritten into anything useful. Ln of t is already a basic function. This second one, what's inside cannot be rewritten into anything better. T squared plus 3, there's no multiplication. It's t squared plus 3. There's no division. There's no power being applied to the entire thing. Yes, there's a t squared, but the square is being applied to t, but it's actually t squared plus 3. The plus causes a problem. We cannot split this using the rules unless it's being multiplied the entire thing, being divided the whole thing, or being powered the whole thing. So it turns out this is as far as we can rewrite it, and this is what we refer to as logarithmically simplified. Simplified. It's as far as we can take it by reducing it with natural logs. And even on the previous one, as you saw, sometimes things can factor and stuff to be written even farther, but usually those are optional things. I've gotten as far as only having to use one rule, the u prime over u. And that's usually a good indication of where I could probably stop. Up here, I'd still have a chain. Up here, I'd still have a product and a chain. And so each time I reduce how many steps I'm going to do it, and therefore make the problem easier. Now let's actually take the derivative. So I do d dt, because we're doing the derivative with respect to t now, of the natural log of t plus 3, the natural log of t squared plus 3. Now, remember, this derivative essentially distributes because they're being added. So I'd have the derivative with respect to t of ln of t plus the derivative with respect to t of 3 ln t squared plus 3. The 3 is going to pop out front and not do anything. Use the basic derivative rule to simplify the first one. The derivative of the natural log of a variable is 1 over the variable, plus the 3 moves out front, and then we do u prime over u. U prime over u. So u prime would be 2t over u, t squared plus 3. And now we should algebraically simplify as much as we can. In this case, 1 over t plus the 3 can multiply to the 2 and give me 6t over t squared plus 3. And this is considered algebraically simplified. Could I have combined those together using more algebra rules? Yeah, but there's no real need to, especially if I was about to be asked to take another derivative. So if I wanted to do like a second derivative test or something to find things like concavity, remember? This was a terminology from chapter 3. Well, I'd rather leave it here. This is just nice to work with in almost every respect. So that's number 56. Same basic concept as the previous ones, using logarithmic rules to rewrite the function into a significantly better form, and then use that to get to a solution. Okay. Now let's look at 58. Okay, on 58, we have f of x is equal to the natural log of 2x over x plus 3. Okay, let's talk about how to algebraically and logarithmically rewrite this function. So step 1, I have division. Division can become subtraction. Cool. Now, I can actually go farther if I wanted to, right? I have multiplication in this one. 2 times x. I have one thing times the other thing with no other operations involved. So I could split this, but for reasons I'll explain in a moment, it's not really that helpful. But if you want to see it, I will do that at the bottom here in just a little bit. And so I'll save that for a rainy day. Okay, let's do this. So for each one of these, I'm going to do u prime over u prime over u for each one, and then get a solution. So for these ones, I'm going to do d dx, since we're dealing with x, of the natural log of 2x minus the natural log of x plus 3. And then I do u prime over u. So if I do u prime, the derivative of 2x is 2 over u, which is 2x, minus the derivative of x plus 3 is 1 over x plus 3. And then I should algebraically simplify as much as I can. The 2 and the 2 will cancel, leaving me with 1 over x minus 1 over x plus 3. And that's as far as it can simplify, at least easily. So we followed our rules, and we got to a solution that is algebraically simplified. This is right. Now, I want to showcase that we will get the same answer if we use the properties another time. So there's one other way I could rewrite that original function, ln of 2 plus ln of x minus ln of x plus 3. This statement is equivalent to that top one. The reason being, 2 times x, the multiplication becomes addition, so 2x added. And the subtraction is still being subtracted, everything looks good. If I then take the derivative with respect to x, some unique things happen to make sure I get this exact same solution. First thing, the natural log of 2 is a number. This is a number. So when I take the derivative of a number, I get 0. Plus the natural log of x. Well, natural log of x is 1 over x. Minus natural log of x plus 1. Then we do the u prime over u just like before. 1 over x plus 3. And lo and behold, these two are equivalent. It's because the rules make sense. Like, they have to work. There's no way around that fact. And so no matter which way you do it, you will get the exact same solution. Even if you were to take a direct derivative using this problem and the chain or the quotient rule, because you have two things being divided, you will eventually get to this solution. It just may take a lot of algebraic work to get there. And by comparison, the algebraic work to get to here is very simple. But you'll notice that while the work is simple, you must know the rules. And so if you don't have the rules memorized, as is very uncommon, I would suggest taking the time to write out the rules in your notes somewhere that you can keep track of for this chapter. Because this chapter is all about exponential and logarithmic and other interesting functions. So not having these rules memorized can be a significant handicap if you're not prepared. So this was 3 examples to help prep us for our work today. Most of these were reviewed from last time, so that was good work. Now let's talk about the 2 things we actually need to discuss for today. Okay. We have 2 new topics. These new topics deal specifically with what I like to refer to as complex logarithmic differentiation, which is fun is not the right word. Fun is actually the opposite word I would use, and I love this stuff. It's interesting in a very boring way. And then we have what's referred to as absolute value logarithmic functions, which are the last couple problems that you're going to have to deal with that are not in that other category. So let's take a look at some of these functions and figure out how to approach them. So in our notes and in the text, let's go back up. And we are actually right here. Example 6. Logarithmic differentiation. The idea here is you can use a log to solve a more complex problem. And usually these do not have a log already in them. At the beginning. If we take a look here at example 6, you'll notice that this problem does not have a log anywhere in it. Nowhere in this problem is there a logarithm, but it is nasty. And so logarithmic differentiation is a unique way to solve very nasty problems. Okay? We're not talking your mama here. Okay, we're talking nasty, bad. If you look at number 6 and I said take the derivative, you would have a quotient rule with a chain on top, a chain on bottom, with a chain inside of it. It is nasty to do. And so for a second, I'm going to showcase exactly how to do this problem using old rules that allow us to actually solve this thing by standard techniques, and then use a logarithm to get to the solution much easier than normal. So let's take a look at the function. And here we have y equals x minus 2 squared over the square root of x squared plus 1, and with x not equal to 2. The reason x cannot be equal to 2 will become apparent later, because it actually breaks the function down a little bit whenever we actually do the logarithm. So there we go. So in this problem, it's a nasty derivative, right? I don't want to solve this by standard techniques. And so I'm going to use logarithmic differentiation to do so. How do I do that? So step 1. You're going to natural log both sides. You can, in algebra, add to both sides, subtract to both sides, multiply to both sides, divide to both sides, power both sides. You can do trig functions as long as you do it to both sides, and you can do logarithms to both sides, meaning I can rewrite this function as ln of y equals ln of x minus 2 squared over the square root of x squared plus 1. This is algebraically allowed as long as I do it to both sides completely. So ln of y equals ln of this. The reason I would want to do that is twofold. One, it's going to make this side simplify easily using properties of logs. And two, the left-hand side, while it looks worse because I can't get y prime easily, I can still get it using the same theorem I've been using the whole time, that u prime over u, which is really helpful. So let's take a look at this function, and let's show some simplification. Left-hand side's ln of y. The right-hand side, I have division. Division becomes subtraction, so this will become ln of x minus 2 squared minus ln square root of x squared plus 1. I can rewrite again. This time I'll use a power rule to bring both of these pieces out. This becomes ln of y equals 2 ln of x minus 2 minus the power becomes a 1/2 and is brought out front, ln of x squared plus 1. If I'm looking at this problem now, like, this side is so much easier to take the derivative of compared to the original function, right? Look at this original, and then look here. The take derivative of this one, I would just have to do u prime over u, and don't forget the 2 out front, that's not too bad. And then to do this one, I would have to do u prime over u as well. And like, this is like a 5-second problem compared to this one. Remember, this one would take a long time to get the solution to. The only problem is this ln of y. Thankfully, I can use the same property that I've been using the whole time to fix this side, but it has something interesting happen. Ready? So now I'm going to take the derivative with respect to x. Now when I do that, give me a second. When I do that, it's going to force the right-hand side to do exactly what I expect. But on the left-hand side, I'm going to get something referred to as implicit differentiation. What it means is you're going to have y and y prime in the same problem, not just y prime like we normally get. Because remember, if you think back to some of the other examples we've done, right, as we've done them, y becomes y prime eventually, because it just does. We take the derivative of both sides, and when we do, y becomes y prime. But in this example, that can't happen. It doesn't happen. Like, it just doesn't, because on the left-hand side, we don't have y by itself. So we have to take the derivative of this left-hand side by the same rules and properties we do it with the right-hand side. So let's do that. If I use ln of y, I would use u prime over u. So this would become y prime over y. On the right-hand side, the 2 doesn't do much, but the ln becomes 1 over x minus 2. The minus 1/2 doesn't do much. And then on the other side, x squared plus 1, u prime would make this a 2x, and then u would make this an x squared plus 1. So we end up with y prime over y equals, the 2 would move on top, so 2 over x minus 2, minus the 2 and the 2 will cancel, leaving me with x over x squared plus 1. So there we have it. Now, I don't want y prime over y. I want just y prime. So using an algebraic property, I'm allowed to multiply to both sides of an equation, and I'm going to multiply by y. When I do so, I get the following new equation. Y prime equals y times 2 over x minus 2 minus x over x squared plus 1. Why is that useful? Why is that better? Well, it turns out there's one final trick to this method, and this is a trick that you will use every single time in your homework. We already know what y is. We've known what y is the whole time, because y was given to us at the beginning of the problem. we know y is equal to this equation. And now I can do my last step, which is a basic substitution. Y prime is equal to x minus 2 squared over the square root of x squared plus 1 times 2 over x minus 2 minus x over x squared plus 1. Now your book does go farther to simplify this quite a bit more. I don't see that as necessary. It says find the derivative. This is the derivative. And you know me, I prefer to always get to my solution by the best steps possible without needing to go in the wrong direction. So this is as simplified as I care to take it. Now, algebraically, you don't like running around with the radical down. Like there's all kinds of little things that you could improve on this problem. But this is perfectly acceptable. So, there we have it. This is just one way in order to take a unique derivative. It's referred to as logarithmic differentiation. We use a log to solve a more complex problem, and it usually does not have a log in them to begin with. But it's usually because the problem is nasty. We look at this problem from example 6. It's nasty. We don't want to take this derivative by standard techniques, even on our best days. And so we instead rewrite the problem and solve it manually using different steps. Now, it does look like a lot of work here. However, you must always keep in mind how much work would this have been, and how likely are you to make a mistake. These steps are a lot of them, but they're simple. They are rewriting using rules, and then taking a derivative that's very simple, and then rewriting using rules again. By comparison, I'm going to make up a number. You are 95% less likely to make a mistake here than you would be trying to do it here. Just made up number, 95%. You know what? It's 96. 95 is too round. 96% more likely to make a mistake here. 96% less likely to make a mistake here. To finish, there's one last rule to talk about. It's right here. It states that if u is a differentiable function and u does not equal 0, then essentially the absolute value doesn't matter. And so if you look here, if we have the natural log of cosine, then we just let our u equal cosine. And so we get negative sine over cosine, which becomes negative tangent using properties. And so like this is really helpful. The last thing I'll mention is there are color problems that ask you to find things like relative extrema. Don't forget, as part of our notes, a reminder. If the problem says find relative extrema, it just means take the derivative and equal it to 0. That's all relative extrema means. Solve it by setting it equal to 0. And if I look in your homework, there are a couple that ask you to do that. Locate any relative extrema. That's one of your homework problems. There's also one in here that asks you to find the equation of a tangent line. Here it is. These ones. These equations of a tangent line. To find a tangent line, remember, you find slope by plugging into the derivative. And then you plug m and the point into y minus y1 equals m x minus x1. That was awful. I'm sorry. Y minus y1 equals m x minus x1. This is all back from chapter 3. It's been a little while, but once you see a couple of them, it makes a lot of sense. But there you have it. If it talks about relative extrema, it just means take the derivative and set it equal to 0. If it talks about finding the tangent line, it just means plug into the derivative and then plug that into slope, point slope form. Your homework is relatively short, 55 to 73 odds. It's a pretty short assignment. It's about 11 problems. There are 4 problems here, 5, 6, so it's about 17 problems in total, and they will be due tomorrow night. To finish up today, if you have any questions on this first assignment, either from yesterday or today, please feel free to shoot me a message, and I will address any questions you have on Saturday and a short video. And that'll be it. If you need any help with anything, make sure you get that question to me. And if you want something more specifically explained, you can ask that too. And I will produce a video tomorrow and post it before the homework is due. That's it for today. Remember, make sure you get your homework done, and the test should be graded by the time you go to bed tonight. So I will talk to you guys later.